I'm Almighty God. I'm Master Sankoshi, and today I want to talk about Introduction to AC/DC Module. The resistive part of the coil impedance peaks at the resonance frequency. The reactive part of the coil impedance approach the one given by the static inductance value at low frequency. With increasing frequency, the quantity increases and then changes sign at the resonance. This happens since the inductor is entering a capacitive regime where the net current is dominated by displacement currents flowing perpendicularly to the coil windings. As a final step, pick one of the plots to use as a model thumbnail. This selects a nice looking two-dimensional figure for the graphics window. In the model builder window, under the results, click absolute bezel and coil direction. Click the root node, the first node in the model tree in the settings window. For root under presentation, then select thumbnail, click set from the graphics window. Make adjustments to the image in the graphics window using the toolbar button until the image is one of that is suitable to your purposes. Tutorial 3: Electrical Heating in a Bus Bar. This tutorial demonstrates the use of multiphysics modeling. In Computer Multiphysics with AC/DC module, you will learn how to use one of the many pre-configured multiphysics combinations. The model that you are about to create analyzes a bus bar designed to conduct a high amount of direct current in an industrial setting. See pictures below. So the current conducted in the busbar from bolt 1 to the bolts 2A and 2B produces heat due to the resistive losses, a phenomenon referred to as Joule heating. The busbar is made of copper, while the bolts are made of the titanium alloy. Busbar bolts are usually made of steels, but in this example, we will assume a highly corrosive environment, therefore a titanium alloy was chosen. Under normal operational conditions, the result currents are predominantly conducted through the copper. This example, however, illustrates the effects of an unwanted electrical loading of the busbar through the bolts. The fact that there are different materials is important because titanium has a lower electric conductivity than copper and will be subjected to a higher current density. The goal of your simulation is to precisely calculate how much the busbar heats up. The Joule heating effect is described by conservation laws for electric current and energy. One solved for the two conservation laws gives the temperature and electric field respectively. All surfaces except the board contact surfaces are cooled by natural convection in the air surrounding busbar. You can assume that the exposed parts of the bolt don't contribute to the cooling or heating of the device. The electric current flowing through the upper right vertical bolt surface is 160 ampere, and the potential at the two horizontal surfaces of the lower bolts is 0 volt. Now I want to go through the model results. Note that these instructions are for the used interface and Windows, but apply with minor differences also to Linux and Macintosh users. To start the software, double-click the console icon on the desktop. When the software opens, you can choose to use the model results to create a new console multiphysics model or blank model to create one manually. For this tutorial, click the model result button. If Console Multiphysics is already open, you can start the model result by selecting New from the File menu and then click Model Results. The model results guides you through the first steps of setting up a model. The next window lets you select the dimension of the modeling space. In the Space Dimension window, click 3 dimension. In Select Physics to read under AC/DC, expand electromagnetic heating and still select Joule heating. Click Add, then click Study. In the Study selection window, under General Studies, select Stationary and click Import. Importing the geometry. The next step is to create your geometry, which also you can also can be imported from an external program. Computer Multiphysics supports a multitude of CAD programs and file formats. In this example, import the geometry sequence from the Computer Multiphysics file format. Note that the location of the files used in this exercise varies based on your installation. For example, if the installation is on your hard drive, the file paths might be similar to C program files. Comes to 64. Multiphysics applications in the geometry toolbar, click the insert sequence, then navigate to your console multiphysics installation folder. Locate the subfolder SLC module, introductory electric currents, and double click the file busbar terminal geometry sequence MPH. In the geometry toolbar, click the build on. Global definitions parameters. It is good modeling practice to gather constants and parameters in one place so that you can change for them easily. Using parameters will also improve the readability of your input data. The following parameters will be defined: the maximum element size mh or heat transfer coefficient HTC, and terminal current, which is showed by I. In the model builder window, under the global definition, select parameter 1. In the setting window for parameters, look at the parameters section. You will find some parameters in the table. The parameters are used for building the geometry and they are imported together with the geometry sequence. In the table, add the following parameters for maximum element size. You can enter the value 0.003 meter. Heat transfer coefficients, you can enter 5 watt per square meter Kelvin. For terminal current, also you can write the 160 ampere. The third column, the table is filled out automatically. The final part of the table is shown below. You see we have a length, a bolt radius, a thickness radius, width, maximum element size, heat transfer coefficient, terminal current, and material sections. Add material. In the home toolbar, click add material to open the add material window. Go to the add material window. In the tree, select built-in and select Cooper. Click add to the component in the window toolbar. In the tree, select built-in titanium beta 21s. Click add to the component in the window toolbar. In the home toolbar, click the add material to close the add material window. Materials section. Select titanium beta 21s or matte SE and select domains 2 till 7 only. In the settings window for material, locate the geometry into the selection section. Click the create selection. In the create selection dialog, type titanium boards. In the selections name text field, click OK. Now I want to go through the heat transfer installers. In the model builder window, under the component bar, right click heat transfer installers and choose heat flux. In the settings window for the heat flux, look at the boundary selection section. Select the all boundaries except for 8, 15, and 43. Note that there are many ways to select geometry entities when you know the boundaries to exclude, such as in this exercise, you can select all boundaries and then remove the corresponding boundaries. In this example, select 8, 15, and 43 in the selection window and click remove from the selection. You will also notice that there are some interior boundaries such as 9 to 11 that are marked as not applicable. For more information about selection geometric entities in the graphic window, see the Computer Multiphysics Reference Manual. Locate the heat flux section. From the flux type list, choose convective heat flux in the H text field, type HTC. In the model builder window, under the component 1, click electric boundaries currents, so boundary terminals 1. In the physics toolbar, click boundaries and choose boundary terminal. Select boundary 43 only. In the settings window for the terminal, locate the terminal section. In the I0 text field, type I. The settings of the boundary terminal 1 are shown in the figure to the right. Next, make similar settings for boundary terminal 2. Boundary terminal 2 sections in the physics toolbar, click the boundaries and choose boundary terminal. Select boundaries 8 and 15 only in the settings window for boundary terminal. Locate the terminal section. From the terminal type list, choose voltage. In the V0 text field type 0. Mesh chapter. The simplest way to mesh is to create an unstructured tetrahedral mesh which is perfect for this model. A physics control mesh is created by default. In most cases, it is possible to skip to the study node and just solve the model. For this exercise, the settings are investigated in order to parameterize the mesh settings. The first step in the mesh toolbar, click the tetrahedral. In the model builder window, click the size. In the setting window for size, look at the element size section. Click the custom button, look at the element size parameter section. In the maximum element size text field, type MH. In the minimum element size text field, type MH minus MH divided by 3. In the curvature factor text field, type 0.2. In the mesh settings window, click Build All. The mesh is shown blue. And you see, we are in the near the poles. We have a more distributed and more nodes based on the finite element method. Study and results. In the home toolbar, click Compute. The study node automatically defines a solution sequence for the simulation based on the selected physics and study type. In this case, the simulation only takes a few seconds to solve. During the solution process, two convergence plots are generated and are available from the tabs next to the graphic window. These plots show convergence progress of the different solver algorithms engaged by the study. Once it is finished, several default plots will show under the results node. Temperature section. Select the temperature based on the HT plot group under the results node. Click the Zoom Extents button in the graphic toolbar. For volume, in the model builder window, expand the temperature node, then click volume. In the settings window for volume, click the expand range selection, select the manual color checkbox. In the minimum and maximum text field, type 324 in the temperature. H2 toolbar, click plot. Click the zoom extents button in the graphics toolbar. Note that the temperature distribution is laterally symmetric with a vertical mirror plane running between the two large titanium boards and cutting to the center of the upper plot board. In this case, the model doesn't require much computing power and you can model the entire geometry. For more complex models, you can consider using symmetries to reduce the computational requirements. Thank you so much for watching my tutorial video until the end, and also you can download proper, appropriate and related console multiphysics simulation file from my github.com/masterscript. Today is the first day of the June and 2026. Time is 3:29 in the morning.